What if the world's biggest living things, trees that weigh as much as 10 blue whales, aren't actually taking anything from the ground beneath them? And what if pretty much everything you learned in school about where a tree's bulk comes from is totally upside down? The real reason you don't see giant holes around ancient forests isn't just a quirky detail. It's actually the key to one of the wildest and most beautiful tricks nature ever pulled. Here's the thing. We're diving into a question you probably never thought to ask. But once it's in your head, good luck letting it go. Why don't trees leave holes in the ground? Seriously, picture it. A giant sequoia can tip the scales at over 2,000 tons, the same as 10 blue whales, the biggest animals that ever lived. If you plopped a blue whale down in one spot and left it there for a lifetime, it would tear up everything around it. You'd see a crater, a wrecked patch of earth, a spot that looked like it had been vacuumed clean. But trees? They stay put for centuries, getting bigger every year, and the ground around them? Flat as a pancake. No holes, no craters, no sign they've taken anything at all. It's the kind of thing that's almost too obvious to notice, but once you see it, you want to know why. The answer turns out to be one of the most mind-bending stories in biology. You get experiments from the 1600s, wild chemistry under your feet, and a peek into how the carbon cycle keeps life on Earth rolling. Let's cut right to it. What's a tree actually made of? If you had to guess, you'd probably say dirt. Trees grow from the ground, right? Their roots are buried in soil, and their trunks shoot up from the earth. It just feels obvious. They must get their mass from the dirt. But nope. That's one of the biggest misunderstandings in biology. The proof? It goes all the way back to the 1600s and a scientist named Jean-Baptiste van Helmont. He was one of the first to really test how plants grow. His experiment was simple but brilliant. He took a willow sapling, weighed it, and planted it in a pot with a carefully measured amount of dried soil. He covered the pot so nothing else could get in, and watered it only with rainwater or distilled water. No fertilizer, no extra dirt, nothing fancy. Just water and the original soil. For 5 years, Van Helmont looked after that willow. He kept it watered, safe from pests, and watched it grow. After 5 years, he pulled out the tree, dried the soil, and weighed everything again, just as carefully as before. And what he found blew his mind. The willow had gained more than 160 pounds. It grew from a twig into a small tree. But the soil? It barely changed, just a couple of ounces lighter. So where did all that new tree come from? It didn't come from the dirt because the soil was basically the same. And even though he'd added way more water than the tree's weight gain, water doesn't just turn into wood. Van Helmont figured the tree's mass must have come from the water. He wasn't totally right, but he was a lot closer than anyone who thought trees ate dirt. The real answer is even crazier. Most of a tree's mass comes from thin air. For real. Let's break that down because it sounds like a magic trick, but it's just science. Here's how it works. Trees, and all plants, have tiny pores in their leaves called stomata. These little mouths open and close, letting gases move in and out. On the underside of every leaf, there are thousands of stomata, always breathing. Through them, trees pull in carbon dioxide from the air. Now, carbon dioxide, CO2, is just a tiny slice of the air, only about 0.04%. It's invisible, you can't smell it, and it seems like nothing. But it's absolutely crucial for life on Earth. Inside the leaf, sunlight hits the green chlorophyll, and the tree uses that energy to combine the carbon dioxide from air with water sucked up from its roots. Through a bunch of chemical reactions, the tree turns these ingredients into glucose, a simple sugar, and spits out oxygen as a bonus. Glucose is where it all starts. The tree takes those simple sugar molecules and starts building. It links them into cellulose, the tough stuff that makes wood strong. Then it makes lignin, which locks everything in place and keeps the wood rigid. Hemicellulose, pectin, and a whole mix of other organic compounds come next, making up the bark, branches, leaves, and roots. Every part of the tree, right from the highest twig to the deepest root, gets built mostly from carbon that used to be floating around in the air, invisible. Just think about that for a second. The wood in your table, the paper you scribble on, the thick trunk of some ancient oak, they all started as carbon dioxide drifting through the sky. The tree turns air into something solid. It's actually a monument built out of the atmosphere. That's why you never see pits or holes around trees, like you might expect if they were pulling their mass out of the ground. They're not digging up the earth for their substance. They're mining the sky. Trees pull what they need from the endless supply in the air, not from the limited stash in the soil. A huge tree, weighing a couple of thousand tons, has had to pull an insane amount of air through its leaves to get that big. To put just 1 ton of carbon into its body, a tree needs to sift through about 6,000 tons of air. That's around 5 million cubic meters. Imagine filling 2,000 Olympic-sized swimming pools, and all that air gets processed by one tree, just to grab a single ton of solid stuff. Now picture a whole forest at work, and you start to see just how massive and important this air filtration operation really is. The tree's canopy is built perfectly for the job. One big tree might have tens of thousands of branches and millions of leaves, all working at once to filter the air. Each leaf is thin, with as much surface area as possible, soaking up sunlight and breathing in the atmosphere. Those veins you see in a leaf aren't just decoration. They're pipelines, delivering water and nutrients to the cells where photosynthesis takes place, and shipping sugars out to the rest of the tree. Leaves don't just grow anywhere either. They're arranged to catch the sun without blocking each other, almost like a field of solar panels, each one angled for maximum light. The tree pours a ton of energy into this leafy crown because it's the engine that keeps everything running. No photosynthesis, no food, no tree. But there's more to the story than what's happening above ground. The roots matter just as much, and they're a lot more complex than people tend to think. Most folks picture roots as mirror images of branches, diving deep into the earth. But really, most roots don't go that deep at all. About half of a tree's roots are in the top 10 inches of soil, just 25 centimeters. They spread out wide, sometimes stretching 2 or 3 times farther than the branches reach overhead. This shallow, sprawling network works because the topsoil is where the good stuff is. That's where organic matter breaks down, where minerals get released, where water hangs out after a rain. By spreading out near the surface, trees scoop up what they need without wasting energy digging deep into poor soil. At the very tips of the roots, you'll find root caps, protective little helmets that let the root push through dirt without getting hurt. But root caps do more than just protect. They've got cells that sense gravity, so the root always knows which way is down. They can also pick up on temperature, moisture, even certain chemicals in the soil. One tiny root tip is like a high-tech sensor, scouting out the best route toward food and water. Right behind the root cap is where the action happens. Cells expand and divide, pushing the root a little farther into the earth. A bit farther back, you get the root hairs, tiny threads that explode the surface area for soaking up water and minerals. Billions of these little hairs work nonstop, absorbing what the tree needs. They're fragile and don't last long, constantly dying off and getting replaced. But without them, the tree wouldn't last. They do the essential job of pulling in water and nutrients from the soil. Here's where things get really interesting. Even with all their tiny hairs and branching tips, roots can't go everywhere. There are these minuscule cracks and pockets between grains of sand, silt, and clay in the soil, so small, not even the skinniest root hair can squeeze in. Yet those tight spots are packed with water and nutrients the tree desperately needs, but just can't reach on its own. So, trees did something wild. They struck up a partnership straight out of sci-fi. they joined forces with fungi. This relationship is called mycorrhizae, Greek for fungus and root. It's ancient, like almost 500 million years old. Plants and fungi have been working together since plants first crawled out of the water and onto dry land. Honestly, if they hadn't teamed up, the world would look nothing like it does now. Here's how it works. The fungi actually grow right into the tree's root cells, weaving together so closely that they create a super efficient network for swapping nutrients and sugars. The fungal hyphae, imagine threads hundreds of times thinner than a human hair, slide into those microscopic soil spaces roots can't reach. These threads fan out in every direction, mapping the soil in ways roots never could, building an invisible web beneath our feet. The hyphae break down minerals and bits of organic matter, pulling out phosphorus, nitrogen, potassium, all the good stuff a tree needs to thrive. They can even tap into forms of nutrients that plants alone just can't access. And in return, the tree sends some of the sugars it makes during photosynthesis straight to the fungi. Sometimes that's up to 30% of everything the tree produces. It's a straight-up trade. Food for minerals, and both sides win big. Some fungi even wrap themselves around root tips, forming a protective shield against nasty microbes lurking in the dirt. Others dive right into the root cells, making elaborate structures that ramp up the exchange between tree and fungus. This partnership is so vital that most trees can't make it without their fungal friends. Stick a tree in sterile soil with no fungi, and it'll barely grow. Honestly, it'll probably die. Fungi aren't optional. They're as crucial as roots or leaves. But there's more. This fungal network does something almost unbelievable. It links trees together. Fungal hyphae can stretch for miles, connecting dozens or even hundreds of trees into a kind of living web. Picture a tree basking in sunlight, making sugar like crazy. Through the fungi, it can send some of that sugar to a neighbor stuck in the shade, struggling to get by. When a tree is dying, it can funnel its remaining carbon to others nearby, a final gift. Scientists have even discovered that trees send warnings to each other through these underground connections. If one tree gets attacked by pests, it can deliver chemical alarms through the fungal network, telling its neighbors to beef up their defenses. So, a forest isn't just a bunch of trees fighting over sunlight and water. It's a community, plugged into an underground internet of fungi, sharing resources and information in ways we're only starting to figure out. They call it the Wood Wide Web, and it's turning everything we thought we knew about forests upside down. All right, back to the water cycle, because this is where trees really show off. A big tree can haul up tens of liters of water from the ground every single day. That water races up through the xylem, the tree's natural plumbing, a maze of tiny tubes stretching from root tips all the way to the highest leaves. The whole system runs on evaporation at the leaf surface. When water evaporates from the leaves, it creates a pull strong enough to lift water against gravity. If you tried to build a pump that powerful, you'd need thousands of pounds of pressure. Trees just do it, no sweat, thanks to the physics of water sticking to itself and the walls of those tiny tubes. So the water travels up the trunk, through the branches, and out to the leaves. And then, almost all of it, about 95%, escapes through little pores called stomata under the leaves. The tree only keeps a tiny bit for photosynthesis. The rest just flows through, non-stop, from soil to sky. As sunlight hits the leaves, that water leaves as an invisible vapor, wrapping the tree in a gentle mist. One large tree can send hundreds of gallons of water into the air every day. That moisture rises, cools off, and turns into clouds. Those clouds bring rain, and that rain keeps the cycle going, pouring back down to refill the roots below. Trees really do make their own weather. They don't just grow in a climate, they help create it. A forest isn't just sitting there, adapting to conditions around it. It's busy shaping those conditions, tweaking temperature, humidity, and even how much rain falls. Take the Amazon. About half the rain that falls there actually comes from the forest itself. The trees pull water up from the ground, send it into the air, and that water falls back down as rain. It's a self-sustaining cycle. So when people cut down trees, it's not just the trees that disappear. The whole water system gets thrown off. Suddenly, there's less rain. The land dries up. Crops don't grow. Rivers shrink. In some parts of the Amazon, this is happening now. Rainfall is dropping so much that rainforests are turning into savanna, dry, open grasslands. And once that process starts, it's almost impossible to reverse. Now, let's get back to that old question. Why don't you see holes around trees, like they've eaten up all the dirt beneath them? It's because trees aren't gobbling up the soil. They get their bulk from the air and water. They team up with fungi to snag tiny nutrients from the soil, way too small to leave any visible gaps. The tree's trunk, its branches, its leaves, all that mass is mostly made from carbon dioxide pulled out of the air, mixed with water, and locked in place by sunlight. The soil? It's there to hold the tree up, to provide water and trace minerals, and to host the fungi that keep the tree healthy. But the soil isn't what makes up most of the tree's mass. Trees aren't dirt eaters. They're air processors, water movers, and fungal partners. They're living structures built from invisible gases, turned solid by sunlight. This changes how we should think about forests. When you look at a tree, you're looking at solidified atmosphere. That carbon was once floating around, heating the planet, and now it's locked away in wood. That's why forests are such powerful carbon sinks. They pull carbon dioxide out of the air and store it for years, even centuries. A single big tree can stash away as much carbon as a car pumps out in a year. A whole forest? Millions of tons. This system doesn't need any fancy tech, no energy input, no maintenance. All it needs is for us to let the trees keep standing. But if we burn wood or clear forests, all that stored carbon is released right back into the air. Centuries worth of carbon, gone in a flash, speeding up climate change. So protecting forests isn't just about saving beautiful places or wildlife, though those are important. It's about hanging on to one of the best carbon capture systems on the planet. It's about keeping that carbon out of the atmosphere, where it does real damage. Next time you walk in the woods, take a second to think about what's really happening. Those trees aren't anchored in the soil the way we once pictured. They're tied to the sky. Their mass comes from the air. The ground isn't getting used up because it was never the main source of their growth. Trees are sunlight and air made solid, connected underground by a web of fungi, busy shaping the climate above. And that's why you don't see holes around trees. But let's push this idea further. As we pump more carbon dioxide into the air, trees are growing faster than ever. It sounds like good news. Forests are absorbing more carbon, slowing climate change. But there's a catch. Fast-growing trees in a high CO2 world often have weaker wood. They're bigger but not tougher, and that makes them easy targets for storms and pests. They also need more nutrients from the soil, which aren't always there. Add in extra stress from heat, drought, and wildfires, and you get a very fragile balance. We're messing with a system we don't completely understand. Let's talk about what really happens when trees die. All that carbon they've stored up doesn't just vanish. When a tree falls and starts to rot, or goes up in flames during a wildfire, that carbon goes straight back into the air. Forest fires don't just take out trees. In a few short hours, they dump centuries worth of stored carbon into the atmosphere. That's a big reason wildfires worry climate scientists so much. They don't just wreck habitats, they wipe out years and years of carbon capture in one go. But here's the upside. We're learning more about forests all the time. Researchers map out the underground fungal highways. They measure how carbon moves through a forest. They watch how forests react as the world changes. And over, their findings point to something surprisingly simple. The best way to help forests, and the climate, is to leave them alone. Protect them. Give them space to do their thing. Trees know exactly what to do. They've had hundreds of millions of years to figure it out. Ice ages, warm spells, asteroid strikes, volcanoes. Trees have seen it all and kept going. They adapt, they evolve, they survive. They don't need us to teach them how to be trees. They just need us to stop interfering. So next time you spot a tree, really take a moment. Notice the trunk and realize it's made from the air around you. Look at the leaves and think about sunlight turning into something solid and real. And beneath your feet, there's a hidden web of fungi, connecting that tree to its neighbors, trading nutrients and secrets. That tree isn't hollowing out the ground, it's busy shaping the air. That's the wild part about trees. They're amazing, right out in the open, and now you know the science behind their magic. If you enjoyed this deep dive from the infographics, and if it made you look at a tree a little differently, hit that like button. It helps us out, and it lets us know you're into this kind of content, uncovering the hidden wonders of everyday life. Don't forget to subscribe and tap the notification bell so you don't miss what's next. We've got more on the science of nature, the mysteries hiding in plain sight, and answers to questions you never even thought to ask. And hey, we want to hear from you. Did you realize trees are mostly made of air? What other natural mysteries have you been curious about? Is there something you see every day that just makes you wonder why? Drop your questions in the comments. We read them all, and your curiosity shapes what we make next. Some of our best videos started with viewer questions. If you know someone who loves nature, or someone who could use a fresh perspective, share this video. Maybe it's your friend who's always planting trees, your relative who's worried about climate change, or that coworker who never thinks about the wild world outside. You never know whose mind you might open. That's it for now. I'm Emma Chamberlain, and this is the Infographics. Stay curious, keep asking questions, and remember, the most incredible things are often right in front of us, just waiting for someone to notice. See you next time.